Hello again. This is video lecture 26.1, our first lecture on chapter 26, which is about current and resistance. In fact, in chapter 25, we started a kind of a transition from just theoretical electrostatics to applications in studying electric circuits. Capacitance is an important property of a circuit element, a common circuit element called a capacitor. And now we're going to learn about two other important properties when you study electric circuits: electric current and electric resistance. And today's discussion is about current and a related quantity called current density. Yep, another density. So, section 1 in chapter 26, we will introduce and define the concept of electric current. And then in section 2 of chapter 26, we'll introduce and define the concept of current density. So let's start with just the definition of electric current. And we'll kind of set the scene. Let me expand this view a little bit here. And let me talk about the pictures we see. The first picture is what may seem like a little odd object. It's a kind of a ring made of conducting material, let's say copper. Okay? Continuous ring shape of a conducting material, for example, copper. And if this conductor is in what we call electrostatic equilibrium, which means that none of the free charges inside, which would be electrons, are accelerating, then it must have no electric field in the body of the conductor. Electric field must equal 0. And every point in the body of the conductor and on its surface must have the same value of electric potential in volts. The conductor must be one big equipotential. However, you can, if you insist, cause an electric field to exist inside a conductor. It will no longer be in electrostatic equilibrium, because its free charges inside will be accelerating, but you can have an electric field in a conductor if you want it. And here's one of the most common ways you would get it. You break the conducting ring and you insert a battery or a power supply, an energy source. We'll draw the picture here as if it's a battery. That's the kind of blue rectangle. It's supposed to make you think of a battery. The left end is the high potential end, and the right end is the low potential end. And that battery creates, because of the potential difference, when you hook up the plus end to the minus end with this strip of copper, you create an electric field inside the copper. And the electric field points from the high potential terminal to the low potential terminal, and it follows the shape of the ring. So over here on the left side, the electric field inside points up. Up here on the top part, it points to the right. On the right side, it points down. It just follows the shape of the ring and pointing generally from the high potential terminal to the low potential. Okay, so yeah, you can create an electric field in a conductor if you wish. It's just not in electrostatic equilibrium, because that electric field will exert an electric force on all those free electrons inside the copper. Okay? Now, remember good old F equals QE for the force on those electrons inside the copper, and that the Q of an electron is negative little e, like that, and that tells us that this force that's going to cause our electrons to accelerate, F, because of this negative sign, is opposite to the direction of the electric field in the copper. Okay? So that's why I wrote this right here. Electrons in the copper drift counterclockwise around this loop, opposite to the direction of the electric field, all because of the negative charge of an electron. Now, I should say a word of explanation about that. Drift. That's hiding a lot of details. Because drift in the physics sense means move at constant speed. Yet I just said the electrons are going to accelerate because of this force here we're talking about, because of that electric field, and they will. But what really happens, and we're not going to get into too much of this detail, is that, yes, the electrons accelerate because of this electric field inside the copper, but then before very long, they're going to collide with one of the positively charged ions inside the copper, or a piece of an impurity atom, something in there that shouldn't even be there. That's always going to be there. You're always going to have impurities. Those things scatter the accelerating electron, which kind of takes the wind out of its sails. And then it accelerates again, and then it scatters, and accelerates and it scatters, and accelerates and it scatters, and it does this over and over and over again. And the net effect of that very complicated motion is a drift at constant speed against the electric field. And in this picture, that would mean counterclockwise around the loop. Okay? All right, now, one of the things we're going to think of as electric current, this new quantity for us, is that it is, in essence, electric current is a stream of moving charged particles. And that's exactly what we've got with these drifting electrons. All right, so the drift of these conduction electrons in the copper constitutes what we will call an electric current. But the negative sign on the electrons is a pain. And so it turns out, for reasons we'll be learning, that if you have negative charges, negative little e electrons, drifting, say, counterclockwise in a loop of conducting stuff, that is equivalent to, can be thought of as if you had positive charges plus little e drifting the opposite way, in this case clockwise. Okay? So we're going to say that this drift of these electrons is equivalent to positive charges drifting clockwise. Okay? And that's very important, because that's the way we're going to think about it. Because we just don't want to have to deal with the negative charges that the electrons have. So we're going to think of it as positive charges drifting, at least in this case, clockwise with the electric field, yes? And moving charge particles constitute what we call electric current. Right? And now we're going to focus on the moving positive. We're going to think of it as if we have moving positive particles, and we're going to look at that electric current. Okay? And the symbol for electric current that our book uses is a little I. And so now you'll see in the picture there are a bunch of arrows pointing clockwise around this loop labeled I. That's our current. That is caused by the hooking up the battery to the copper and creating an electric field in the copper. Okay? By the way, this current that we think of coming from the motion of positive charges, even though it's actually negative charges going the other way, when we think of this current as being due to the motion of positive charges, we call it conventional current. That's just a naming convention. And so you'll often hear me talk about conventional current. That means, well, remember, I'm really thinking of it as if it's positive charges. Okay, now, let's give the formal definition of electric current. I just gave you a description of it. All right, I have imagined a mathematical surface that we're seeing edge on. So it's going to look like a line, but it's actually a surface. And it's mathematical, it's not real. Slicing right down through the copper somewhere. I just drew it with a blue line. Okay? That blue line represents a mathematical surface slicing through the copper. And now what I want to do is I want to count the total amount of charge that passes through that surface, positive charge, in a given amount of time. And here's how we're going to think about it. We're going to watch for a tiny amount of time dt, and we're going to count the total amount of charge, and we'll call it dq, that passes through that surface in the time dt. And then by definition, the electric current I through the surface is defined to be the amount of charge, dq, over the amount of time, dt. A ratio of two infinitesimals, dq over dt. Sometimes you'll hear people say, hear them say, it's the rate at which charge passes through a surface, because a derivative is a rate. You can think of it as dq dt. The SI unit of electric current, that's important. Well, it must be 1 coulomb per second, right, based on that definition. But we need to be aware that the unit coulomb per second is given its own name, the ampere, symbol capital A, sometimes abbreviated as amp. But ampere is the name of the unit, SI unit for electric current. And you can think of current as the rate at which charge is passing through a surface. All right, notice in the diagram, as I said, there's a current arrow that's drawn in the direction in which positive charge carriers would move. That's again what I meant by conventional current. Okay? Even if the actual charge carriers are negative and moving in the opposite direction. You won't get into any trouble if you pretend that it's positive charges moving opposite to the negative charges. Here's another important fact, borne out by experiment. The current is the same through any cross-sectional slice through an object. Now this picture down here needs a little explanation. So imagine what you see there is a piece of copper, right? Conducting material. But what you don't see is the rest of the circuit that they haven't drawn. I'll draw it as a circuit diagram. It's more copper wire connected to a battery, like that, so that we have a complete circuit, and that we have conventional current I flowing clockwise around this loop. And up here in our slice we're looking at, the current I is flowing from left to right. And the picture shows on its edge, on its side, so they look like lines, but they're actually surfaces, 3 surfaces slicing through this piece of copper at different locations. One surface, AA prime, slices straight down on that thin section. Another surface, BB prime, slices straight down in this kind of widened section that for some reason is there. And this third surface, labeled CC prime, slices over here at an angle. But all 3 slice all the way through. Okay? What we're saying is that no matter which of these surfaces you were to look at, and you were to ask, what's the total rate of which charge is passing through that surface, whether it's AA prime, BB prime, CC prime, the current will be the same through each. No matter where the slice is, no matter what angle it's at, as long as it slices all the way through. And there are simple physical reasons why that has to be true. Okay? So that the current I through the slice AA prime is equal to the current I through the slice BB prime is equal to the current I through the slice CC prime. First, the reason, conservation of charge. Charge cannot just magically appear or disappear. So any charge that comes in this piece from the left end eventually has to come out on the right end. And 2, like charges repel, exert repulsive forces on each other. So imagine, contrary to what I just said, that the current through the surface AA prime is, let's say, larger than the current through the surface BB prime. Right? That means the rate at which charge is passing through AA prime is larger than the rate at which it's passing through BB prime. Well, that means in this strip of the copper between those surfaces, between AA prime and BB prime, I in essence have more charge in a given amount of time entering than I have leaving. And so there must be a traffic jam building up in that inner area. Charge must be piling up. Okay? But like charges exert repulsive forces on each other, so they're not going to let that happen. Okay? So charges moving through conductors, right, is not like cars on a highway. You can't have a traffic jam in a conductor like this. The current, the rate at which charge passes through a surface, is the same for any surface. Okay? That's a very important thing to remember. Now let's take the definition of current, I, as dq over dt, and let's just kind of turn it around a little bit, because sometimes we'll get this question. So the definition of current says, well, measure the current dq that passes through a chosen surface in an amount of time dt, and I is then dq over dt. And that's how you'll have I. Well, let's suppose we already know the current I. Maybe somebody's already measured it for us and is telling us. And it's quite possible that the current is a function of time. We'll be studying circuits eventually where the current depends on time. All right? So suppose we know the current I and it's a function of time that's passing through some surface S that's slicing through a conductor. We could ask this question. How much total charge delta Q crosses the surface S between an instant t1 and an instant t2? Some finite amount of time, in other words. Okay? So you already know the current. Then you can ask, well, how much total charge passes through the surface in a certain amount of time? And all you have to do, mathematically, is start with the definition of current, multiply both sides by dt, and then integrate both sides. So you have on the left the integral of I dt, and calculus will tell you that that integral on the right just reduces to the integral of dq, which is just a total delta q. And then you just put the limits on your time integral from t1 to t2, and you get this expression right here. Okay? To get the total amount of charge delta q that passes through a surface in a certain time interval that starts at t1 and ends at t2, you integrate the current. Notice that's just based on the definition of current and rearranging it. Now you could have the case where what you have is called a steady current. Then I is constant in time. It doesn't change with time, the current I passing through your surface. Well, then you can bring the current symbol I out front of the integral, and then the integral dt from t1 to t2 is just whatever the delta t is, and you get the very simple result right there. That the total current passing through your surface is delta q is the current I times that delta t, okay, between t1 and t2. Let's do a little quick practice. Okay. Using the concept of electric current and what looks like maybe a weird connection of wires, conducting wires. And we're not seeing all of the parts of the circuit, just a certain area. And what this figure is showing us is in certain wires, what direction the current is in, and what the value of the current is in amperes. So for example, in this wire up here, there's a current of 1 amp going outward that way. In this current wire right here, there's a current of 2 amperes going inward, and so forth. I'm going to focus mainly on this region right in here, where these 3 wires come together, kind of this central section right here. And now I'm going to look at the question that we have. It says, what's the magnitude and direction of the current I in the lower right-hand wire? Right there. Right? That's the one wire segment that they don't tell me the current or give me an arrow. We're supposed to apparently figure out what that current is. All right, well, the physics idea we will use is conservation of electric charge. Charge cannot just disappear or appear out of nowhere. And current is just the rate at which charge is moving. So the bottom line is, whatever total amount of current I have coming into this central junction, I have to have the same total amount of current going out. that is simply based on conservation of charge. So all we're going to do to answer this is we're going to add up all the inward and outward currents in amperes. I'll make a table. Inward current and outward current in amperes. Okay? Let's do the inward. And this diagram takes a little getting used to because we're not used to dealing with circuit diagrams. But I'll show you how to interpret it. I've already given you a little bit of discussion about it. All right, I want all the arrows that point basically towards this center section. That's inward current. So there's an inward current of amount 2 amperes. Okay? There's an inward current because it's coming up, which is going to end up getting it into that center region. So 3 amperes there. There's an inward current because it's going towards that center region. 4 amperes. There's an inward current because it's going towards that center region. 2 amperes. All right, now the other 2 arrows point outward. So let's total, that's all the inward, let's total that. 3, 4, 5, 9, 10, 11. 11 amperes of inward flowing current. So the outward flowing current must also be 11 amperes. So I would like you now to figure out the direction and the size of that current down there. Pause the video, think about it, come back when you have an answer. Okay, you have an answer? What is the outward current? Well, there's that outward current, 1 ampere. And there's that one, 2 amperes, for a total of 3. But I have to have 11. So there has to be a current of 8 amperes flowing outward. And it's got to be in that right, lower right wire, 8 amperes. Okay? So that's all that was about. And that's based on the concept that charge can't just appear or disappear. All right, now here's another concept for us. Another density. We do love densities in physics. Well, they're very handy. And this one is called current density. And current density is, in simple descriptive words, a local current per unit area. You know, whenever you see the word density, that it's a per unit something. It might be per unit length, it might be per unit area, it might be per unit volume. But it's going to be a per unit something. And in this case, current density is current per unit area. So be careful. There's current, which we now have already defined, symbol little I. And now here's a new quantity, current density. New thing that's related to current, but is its own thing. Okay? In fact, it is local current per unit area. So let's define it. Now what the little diagram here shows is, again, a piece of an electrical conductor, like a piece of copper, just a piece of it, that's connected to a complete circuit. We're just not showing you the whole circuit. And in that copper, I'm going to have conventional current, positive charges flowing, at least in this piece, okay, I, from left to right. Okay, all right. Then I'm imagining a mathematical surface slicing straight through. That's what that gray rectangular shape is. It's a mathematical surface slicing through the conductor. And you can see its cross-section there with the dashed line where it intersects the surface of the conductor. And then we're going to imagine breaking up that surface that's now buried down inside the conductor into little patches of area. I've drawn one of them. It's a little tiny area element, dA. It's just a little patch of area, and it's a vector with a direction. dA for that little patch right there. And its direction has got to be perpendicular to the surface in a direction that we choose, either right or left in this case. I've chosen right. All right, I'm now going to define the current density at that location. Current density there, where that little patch is, okay? Symbol, capital J, arrow. Note the arrow. It's a vector. Note we didn't put an arrow on the I symbol for current, did we? Even though there is in some sense a directionality for current, we're not going to think of it as a formal vector. But this new quantity, current density, it's a formal vector. Symbol then is a capital J with an arrow on top. I'll draw it over here, like that. Okay? Here's its definition. First magnitude, then direction part. The magnitude of the current density, J arrow magnitude, is, by definition, the amount of current, dI, going through that tiny area. Okay? It's dI going through that tiny area divided by that amount of area, dA. All right? The amount of current dI through that little patch of area over that amount of area. What's the SI unit of current density? It must be the unit of current, ampere, divided by the unit of area, meter squared. So ampere per meter squared. Now it's a vector, so what's the definition? Another part of the definition is its direction. By definition, the direction of the current density is the direction in which positive charges are moving at that location. Okay? So the current density vector for that little space right there is to the right, because that's the direction the charges are moving. Okay, so we've defined current density with a magnitude and a direction. And you notice that I really just defined it for that one little patch on that surface up there. You got to go through all that for all the points, all the little patches that make up that surface. And it might very well be the case that the current density, the J, can be different at different points on the surface. It's not always necessarily going to be true, but it could be true. If I take a different patch of area down there, right, the direction might be the same, but the magnitude might be different. We'll have to be told in a given situation what's going on with the J. Okay? All right, so that's the definition of J as local current per unit area. Now, what's a common thing that we'll be faced with is this question right below. Suppose we are given the current density at all the points on a surface, like up above, and we are asked to find the total current I through the surface. So we're given J, and we're asked to find I. See, we got these two quantities, I and J. Current I, current density J. They're related. If we give you one, you can get the other. All right, so let's look at this little drawing down here in the lower right. It's another cross-sectional view, slightly different in looking, but it's still of just a conductor that's part of a complete circuit, and we're not showing you the whole circuit. And this conductor has a kind of a constriction in it. It's wider on the left and it's narrower on the right. And there's conventional current I flowing generally from left to right. And it's kind of represented by those so-called streamlines that you see inside the conductor. And then they've drawn two surfaces, mathematical surfaces. You're seeing them on cross-section, so they look like lines. Slicing through. There's one, S1, through the wide area going straight down. And there's another one, S2, through the narrow area at a slant. And they have drawn little patches of area on each one. Like there's a little patch of area with an area vector dA1 and the current density on that surface J1. And there's a little patch of area on the second surface with an area vector dA2. Notice the area vector has to be perpendicular to the surface. So the dA2 there would be up at an angle. And the current density there is this arrow, J2. Whereas it's this arrow, J1, over here. Notice the J1 and the J2 have different magnitudes. How do you find the total current I flowing through either one of those surfaces? You, in essence, take that expression up there that defines J, multiply both sides by dA, and then integrate. But you have to account for the fact that the J and the dA are vectors, and so you get this integral. To get the current through a surface, if you know the current density, you do the integral over the surface of J dot dA. It's another one of those surface integrals. Like when we calculated electric flux through a surface, E dot dA. All right? This is current density, J dot dA. Note, the current through the surface S1 has to equal the current through the surface S2, current I. Even though those surfaces have different areas and the J's are different on those surfaces, you have to end up getting the same I, physically, because otherwise charge is going to be piling up somewhere like in a traffic jam, and that doesn't happen. Now there's one more idea that's worth knowing, and it's very handy when you're studying materials that are conductors. Remember I said that the charge carriers in the conductor, because of the electric field in the conductor, drift. So they move at a constant speed, and it's called the drift speed. And there's a nice little formula for figuring that out. The drift speed of the charge carriers in a conductor. So we're back to another picture showing a part of a conducting wire. That's itself part of a complete circuit. We're just not showing you the whole circuit. And the part of the wire that we're looking at has length L and cross-sectional area A. Okay? So the length, we just chose a certain length, L, to focus on. And if you look on the cross-section of the wire, that's some cross-sectional area A. And then it's got three arrows drawn beneath here, but they're all representing quantities inside the wire. And you can see a few of the pretend positive charge carriers, and they're all drifting to the left in this picture. So there's a drift velocity, VD arrow to the left. There's an electric field in the conductor. That's what's giving us this drift to the left. And there's current, and therefore current density to the left. So I've got three vector quantities in that section of conducting wire, and they're all to the left. What we want is a relationship between the current density, J arrow, and the drift velocity, VD arrow. And I will just tell you what that that expression is, and then we'll show you how to get it. J arrow equals little n times Q times VD arrow. What is little n? Little n is the charge carrier density, the number of free charges per unit volume. SI unit, 1 over meter cubed. It is a property of a conductor. Okay. Q, of course, is the charge of our charge carriers. Probably going to be just plain old little e. Okay. All right, let me show you where that equation even comes from. Okay. All right. First, I'm going to write down the volume of this wire segment that we've highlighted. Well, it's got a length, I'll denote it VOL. It's got a length L and a cross-sectional area A. It would be the total volume between there and there that's inside the wire. Okay? All right. Next, our charge carriers, our positive charges, are drifting at a constant rate from right to left. So I can ask the time for any one of the charge carriers. time for a charge carrier to travel length L. Delta t. Well, if they're traveling at a constant speed, it's the distance over the speed. Notice I'm distinguishing there between speed and velocity, which I'll write like that. L over the drift speed. That's how long it takes any charge carrier to travel the distance L. Next, imagine a cross-sectional slice up here at the left end of this segment. What's the current through that slice? Current. Not current density, current. Through any cross-section, I'll think of the one at the left end. Symbol would be I. Well, I'll measure the total amount of charge delta Q passing through in a time delta T. The delta T I'll use is the one I just used, got up above, L over V sub D, the time for a charge carrier to travel distance L. And then the total charge that passes through will be, in fact, the total charge that was from the charge carriers that was in the conductor in this length L, because that's how much can get through the left end in the time delta T. And the total amount of charge that's from the charge carriers that's in that length L would be the carrier density, little n, that's the number of carriers per unit volume, times that volume, times the charge of each carrier, little e. Okay? So that's my rather straightforward expression for the current through the left cross-section. Let me now substitute in my expression for the delta t as L over Vd. The L's cancel, and the Vd goes upstairs, so I have N, A, E times the drift speed. I've got an expression for the current. And then I can talk about the current density. Now we will assume, okay, that the current density is uniformly distributed throughout the cross-section, okay, so that the magnitude of the current density through our left cross-section is just the total current going through it over its total area. Using my expression for the total current, and then dividing by the area, notice the area cancels, and I have that expression. Now that's for the magnitude of J, and then you could just make it a full vector equation like that. Okay? And so that is a handy little formula for the current density in a conductor, and it depends on several properties of the conductor. Its charge carrier density, the charge that each carrier has. In fact, the most general way to write that is just to put a Q there, where that means the charge of a charge carrier in the conductor, like that, times the velocity, the drift velocity of those carriers. So we will use that quite a bit in this chapter, as you will see when we do through examples and you do homework. So let me just leave you then with a little bit of practice for Blackboard. And it goes like this. Current and current density in a conducting wire. We've got another figure here of a wire segment that's part of a bigger complete circuit. They're just not showing it. Okay? And in that segment, we have conduction electrons. Notice they're marked with a minus sign, and they're moving leftward in a wire. Okay? Electrons moving leftward. Here's the question. Questions. Are the following quantities directed leftward or rightward in this wire segment? The current I, the current density J, and the electric field E. Okay? My hint is conventional current is what we're talking about. Okay? All right, so we'll be talking about this in class, this material, and that's all for this video.